Hello friends, today I am going to say a few words about the distribution of sample data. The basic concept is like this: the distribution is the visual expression of the numerical values of sample data in terms of a table or graph or through a formula. It portrays or reflects the values of the observations and their corresponding frequencies, that is how often they occur. The distribution of census or population data is known as population distribution, and the distribution of sample data is known as sample distribution. An important aspect of the distribution of a quantitative data set is its shape, because the shape of a distribution frequently plays an important role in determining the appropriate method of statistical analysis. To identify the shape of a distribution, the best approach is usually to use a smooth curve that approximates the overall shape. Some common shapes of symmetrical distribution are bell-shaped, uniform, triangular, etc. Similarly, some common shape of asymmetrical distribution is like left-skewed, right-skewed, J-shaped, inverse, J-shaped, bimodal, multimodal, etc. Graphically, it looks like this: bell-shaped, triangular, uniform, reverse J-shape, J-shaped, right-skewed, left-skewed, bimodal, multimodal, etc. So similarly, when the graphical form of a distribution is divided into two parts that are mirror image of one is mirror images of another one is called symmetric distribution. Therefore, bell-shaped, triangular and uniform distributions are symmetric. In practice, we are little bit flexible. Thus, perfect symmetry is not required to classify a distribution as symmetric. The symmetry approximation is more or less enough. Though, if the distribution is not symmetric, it will be either right skewed or left skewed. The right skewed distribution rises to its peak rapidly and comes back towards the horizontal axis more slowly that it has the right tail. Similarly, the left skewed distribution rises to its peak slowly and comes back towards the horizontal axis more rapidly, that is, its left tail is longer than right tail. It looks like this: right skewed, left skewed, normal distribution, skewness is 0. In reality, generally we do not know the population distribution. We use sample distribution to get a rough idea about the population distribution. Since the distribution of sample data selected randomly from a population will approximate the distribution of the population, hence this approximation will be better with the increase of sample size. Therefore, sampling distribution is basically concerned with the relationship between the distribution of the population and the distribution of the sample. In this context, one important concept is random variable. The sample data are nothing but a part of observations of a population random variable. A random variable is a variable which has a numerical value and their corresponding probability side by side, such that the sum of the probabilities is equal to 1. The random variable may be discrete random variable and continuous random variable. The easiest way to convert a random variable into a random variable by calculating its relative frequency, which may be treated as an approximation of its probability, especially for discrete random variable. So, for example, suppose in a class consists of 10 students, the teacher asked, how many pen drives do you have? The response of the students are shown in the following table. These are the number of students, these are the response, this is the number of pen drive 0, 1, 2, 3 and number of students, that means frequency, and this is relative frequency. Relative frequency is nothing but number of frequency by total frequency, that means 10. So 0 pen drive, the relative frequency is 0.1, 2 pen drive, 1 pen drive 0.3, 2 pen drive 0.4, 3 pen drive 0.2. So in this way, number of pen drive, if we treat as variable, random variable, it has the value of the numerical value of the variable and side by side its relative frequency, that means maybe approximation as a probability, is probability. Okay, so if we plot it in this way or through in terms of any the histogram type diagram, we can get a little bit idea that the distribution that sample fits, more or less normal distribution. Now we are coming to the normal distribution is the basis of sampling theory. The other basic distribution, important distributions are standard normal distribution, chi-square distribution, t distribution and f distribution. Okay, if the distribution of a continuous random variable approximately looks like a bell-shaped curve, then we say that the variable follows normal distribution. We know this. A normal distribution generally characterized by its mean and standard deviation. If two different variable follows normal distribution but their mean and variance same, hence the shape or graphical look will be identical for the two distributions. The spread of the bell shape depends on standard deviation of the variable. Larger the standard deviation, more spread out or flatter will be the two tails of the bell shape. It looks like this bell shape. Now in this context, an important concept is associated with standardized variables, is that the z-score or z-score or normal score. If we subtract the values of the normally distributed variable by its mean and divide the mean values by its standard deviation, then it is known as standard normal variate, and its distribution is known as standard normal distribution, whose mean value is 0 and standard deviation is 1. Symbolically we can write xi distributed normally with mean 0 and variance 1. It looks like symmetrical bell shaped like unstandardized normal curve. For example, suppose the mean and standard deviation of a data set of weight of football players of suppose University of North Bengal is 56.4 kg and standard deviation is 2.2 kg respectively. Hence, the standardized variable zi is xi minus 56.4 by 2.2. Hence, we can easily calculate the z-score of any player, suppose player A whose weight is 50.6 kg and another player B whose weight is 60.8 kg, just by putting this value here, and we can calculate and we can say the decision whether the player A's weight is 2.64 standard deviation below the mean, or player B's weight is 2 standard deviation above the mean, just by plotting this value into z-score. This is the total distribution, that means mean value, mean plus 1 standard deviation, mean plus 2 standard deviation, mean plus 3 standard deviation. Similarly, mean minus 1 standard deviation, mean minus 2 standard deviation, mean minus 3 standard deviation. So all the values will lie within these two ranges, within these values. Chi-square distribution. Square of the standard normal variate is known as chi-square variate, and the sum of square up to a certain number, say k, follows chi-square distribution with k degrees of freedom. Symbolically, the zi equals to summation I equals to 1 to k xi minus x bar by sigma square whole square follows chi-square distribution with k degrees of freedom. It looks like this. It starts from origin. Therefore, degrees of freedom is equal to the number of independent chi-square variate. The chi-square distribution is skewed to the right, starts from origin and approaches indefinitely to the right tail. As degrees of freedom increases, it becomes more and more symmetric. T and F distribution. If we generate another new variate which is a ratio of a standard normal variate and a chi-square variate, then it is called a T variate, and the distribution it follows is known as T distribution with some degrees of freedom, say k. The T distribution also look like standard normal curve, but it is flatter than standard normal curve. But if the sample size increases, T distribution approaches to the standard normal distribution. This is T variate, standard normal variate by chi-square variate with degrees of freedom k, and T distribution also with degrees of freedom k. Similarly, F variate is the ratio of two chi-square variate, and it follows the distribution known as F distribution. In other words, if the two random variables follow two independent chi-square distribution with k1 and k2 degrees of freedom respectively, then their ratio follows F distribution with k1 and k2 degrees of freedom. So F variate equals to chi-square variate with degrees of freedom k1 divided by another chi-square variate with degrees of freedom k2. It looks k1 and k2, the 2 degrees of freedom. One is known as numerator degrees of freedom, another is known as denominator degrees of freedom. It will be helpful at the time of taking the table value from F table. So this is the shape of the T distribution, this is the shape of the F distribution. These are the references from the video has been prepared. So thank you, that's all.